Welcome to Math Blossoms, where growing in mathematics is natural. I am the teacher, Miss G, and for today's lesson, we are going to be learning how to solve systems of equations using the substitution method. So let's get started. Okay, first of all, before you watch this video, you may want to go and watch the systems of equations solved by graphing video, because that explains a lot as well. And it's best to learn the graphing method first and then go into the algebraic methods, which are substitution and elimination. This video is just talking more about the substitution, but there is a second video that you can watch after this one about elimination. Okay, so let's go ahead and get going here. Our first question says, how do you solve systems of equations algebraically? And the answer to that would be two main ways. We just talked about that. One is substitution and the other is elimination. So this video is just going to focus on substitution. And then once you're really good at substitution, that's when you should go and look at the elimination video and see what that's all about. Because there are, different times when you'll need one over the other. For instance, substitution is best used when we have equations where one of the variables is already isolated. For instance, these two equations here, the y is already isolated. You've got y equals 9x plus 2, and then you've got y equals 3x plus 10. And both of those equations, which are in slope-intercept form, by the way, the y is already singled out or isolated. And when you have at least one of your equations where one of the variables is by itself like that, you can always use substitution. Okay, so both of these are in slope-intercept form. So here's an example of when I would want to use substitution. Here's one where one is in slope-intercept form and one is in standard form. This is another good time to use substitution. One of these equations is a horizontal line. So if you get like a horizontal line equation, y equals a number, or a vertical line, we call those Vux lines. Those are x equals a number. Anytime you see those, it's a good time to use substitution as well. And then here's two equations where one of the variables is isolated. The x here is isolated on the second equation. So you can use this. This top one here is in standard form, but this bottom one is not really in a specific form. It's not in slope-intercept or standard form, but it does have that x isolated. So you can use substitution when that happens. Okay, so there's just some examples of when it's a good time to use substitution. Okay, so let's try some. So we're going to start with two equations that are in slope-intercept form. And the idea is that we're going to get, the intersection point. We're trying to get that, the solution can be a one solution answer and no solution, a one solution answer when the lines are intersecting, a no solution answer when the lines are parallel, and then an infinitely many solution answer whenever it's a line on top of a line. Remember, because they're sharing all the points when they're on top of each other like that. But their equations will look different. So these are both in slope-intercept form. So if I'm going to solve these, that's the answer that I know I'm going to get, but I just wanted to show you how I'm going to get there. Let's use light blue to start off with. Okay, so what you do is you can take what y is equal to in either of the equation. I'm just going to pick the top one, okay? Y is equal to all of this. So because the x and the y in both equations are representing the same xy point, right? Because we know our intersection point is going to look like that. It's going to be x comma y, right? In our answer. So you can take what y is equal to in the first equation and substitute it in place of the y in the second equation. And the reason you want to do that, I'm trying to draw an arrow, but that arrow did not look like an arrow. There we go. We'll try that again. Okay. The reason you want to substitute it like this, and I'll go ahead and rewrite the equation now, is because when you take that y out and substitute it for what y is equal to in the first equation there, you're not going to have any y's left in your equation. See, when I rewrite this now, all I have are x's in this equation. So once you have gotten rid of one of your variables like that, and you're just left with one variable, the x, you could solve that using your DCMAM steps. If you don't know what the DCMAM steps are, you'll need to watch the solving equations videos on the equation playlist, where there's quite a few videos on that showing you how to solve multi-step equations using the Don't Call Me After Midnight DCMAM steps. And that's just a way to remember how to solve multi-step equations in what order, right? Well, in this one, there's no D and C step because there's no distributive property or combining like terms to be done. But we do have the first M step, which is to move the variable. When there are variables on both sides like this, and you've already done your distributive property and your combined like terms, you need to cancel one of them out. So I'm just going to cancel the one on the right out. It's a positive 3x. So I know I've got to subtract 3x from that to cancel that out. And since it's an equation, I have to do the same action on both sides. And that's going to give me a 6x then. So one of the best practices I always tell my students is when you're done canceling something out, go ahead and rewrite the equation and just leave out the stuff you don't need, right? So we've got 6x over here. We've got a minus 2. My 6's don't look right. There we go. 6x minus 2. That 3x bit is now gone, and all I'm left with over here is a positive 10. Okay, so now we have a two-step equation. And so step A of the Don't Call Me After Midnight is to get rid of the number that is being added or subtracted with your variable. And that's this negative 2 here, this minus 2. So that's why I'm adding a 2. Adding a 2 to the other side of the equation to make that equation balanced. It's going to give me a 12. Again, since I did something to cancel something out, I'm going to rewrite that equation with what's left over. I have 6x on the left side now and only a 12 on the right. And the last step of the DCMAM is to, divide whatever number is being multiplied times your variable. And that would be the 6 here. That's going to give me a 1x. So when you're doing this division at the end, you're not canceling out the x. You're not zeroing it out. You're turning it into 1x because 6 divided by 6 is 1, right? And then 12 divided by 6 here is a 2. So we have half of our answer. We know the x is a 2. And so how do we get the y now? Okay, so here's where you have to substitute a second time. Okay, we substituted all of what y was equal to for that y at the beginning. Now we're going to substitute what this x is equal to in place of either one of these x's in the original two equations we started with. It doesn't matter which one. I'm just going to pick the second one this time. Okay, but you could put it in the first one too. It will still give you the same answer. So if I'm rewriting that second equation, I'm going to write it as y equals 3. But this is 3 times x. And since I'm taking the x out and substituting it with a 2 here, that's going to be 3 times 2 instead. Okay, so all I did was take this x out and replace it with this 2. Okay, and then I'm going to finish writing the equation. I have the plus 10 over here. And so to finish solving this, I need to multiply the 3 and the 2 together first before I add the 10. Okay, and 3 times 2 is just 6. And when I add the 10 to that, I end up with a 16. So my y is actually 16. And that should be my final answer. Let's check ourselves. Yes, that's what we got, 2 and 16. So let's try another example. Okay, this time we have one in standard form and one in slope-intercept form. And so when I do my substitution, I'm going to take what y is equal to in the first equation, and I'm substituting it in place of that y right there. So this is going to look a little different than the first example we did. So when I rewrite this equation, I end up with 5x plus 6, but instead of times y, it's going to be times all of that, okay? So when I have all of that to multiply it times, I need to put all of that into a grouping symbol or a parentheses, because I'm not just multiplying the 6 times the negative x, I'm multiplying the 6 times the 4 as well. So let me go ahead and erase my little dot, because once I put that parentheses there, what just happened? There we go. Once I put that parentheses there, I don't really need a dot, because parentheses next to a number means multiply, right? And so I didn't really need to write that dot, but I wanted y'all to understand why I'm putting a parentheses around it, because this, this whole thing represents y, right? So if I'm, if I'm supposed to multiply this 6 times y, that means I got to multiply that 6 times all of that, right? Okay, and all that's going to be equal to 13, just like it's written down here. So I took out my y and I replaced it with all of that, and I just grouped it into a grouping symbol. Now this time when I solve the equation and I'm using my DCMAM steps, distributive property is in the problem. So I do need to distribute the 6 to the negative 1x. That's going to give me negative 6x. Again, this negative x is really negative 1x. There is a 1 there. They just don't write it. It's an invisible one. 6 times 4 here is 24, positive 24. So I'm going to write it as plus 24. So my distributive property has been done. I'm just going to move my 13 back down here and also move my 5x down here. Okay, so all I've done is distribute, and then the next step is combine your like terms. And I do have some terms on the left side here that I can combine. There's nothing on the right side of the equals that I can combine because there's just a 13 there, but I can combine the 5x minus the 6x here. And 5x minus 6x gives me negative 1x, or just negative x. They mean the same thing. And then I'm just writing the rest of the equation down here. And once again, we have a two-step equation. And so I need to get rid of my 24 before I get rid of my negative 1. Always do the constant before the coefficient. The coefficient is the one that's right next to your variable. That's always the one that's going to go last. You're going to, get rid of that one last. And it's usually through division. But this is going to be subtracting 24 on both sides. And 24 and 13, when I subtract them, I get an 11. Actually, a negative 11. 13 minus 24. And so when I rewrite that equation, I end up with negative 1x equals negative 11. And I realize a lot of this algebraic solving systems of equations, a lot of it is just knowing how to solve a multi-step equation to start with. There's a little, few tricks at the beginning about substituting things in, but you still need to know those DCMAM steps to do this process. The only thing left to do is to get rid of that negative 1, and to do that, I divide. Negative 1 divided by negative 1 is positive 1x, which is what I want. And then when I divide this by negative 1, my negative 11, I end up with a positive 11. So my x value should be positive 11. Now that I have my x value, I need to change colors here. Let's go with dark blue. And we're going to take all of this and substitute it into one of the equations. And this time, I am purposely going to put it into that equation. And the reason why I'm choosing the top equation and not the bottom equation is not because it's going to get a different answer. They're both going to give you the same answer regardless which x you substitute out. But if you notice the top equation, the y is already by itself. So that's just going to make this equation easier to solve. If I substitute this x here, if I put this 11 here in place of that x, there's a lot more that I have to do to solve that equation. But since y is already by itself up here and I'm trying to solve for y, it's easier to solve it when y is already by itself. So I'm going to go ahead and substitute that in. It's going to be y equals negative 11 instead of negative x plus 4. And negative 11 plus 4 is negative 7. So our answer for this should be 11, negative 7. Let's see if we're right. Yes, we are right. Okay, so let's try another one. This time they're both in slope-intercept form, just like we did in the first example. Let's start with red this time. I'm going to take, and again, I could choose which one because they're both equal to y. So I'm just going to take what y is equal to in this equation and substitute it in place of y in that equation. And what I'm going to end up with is plus 5 equals 3x plus 2. And there's no distributive property. There's no combining like terms. But we do have to move a variable because we got a 3x over here and a 3x over here. And this is where we're going to run into some snags on this one, because when I cancel that one out, it's also going to cancel that one out. And I know from previous solving equations and solving systems of equations, when you get both of your variables canceled out and you're left with two unequal numbers, 5 and 2 are unequal to each other, that's going to be no solution. Those are parallel lines. And in fact, I knew that when I first looked at the equations, because if you notice, and we talked about this in the graphing video on systems of equations and also on the perpendicular equation video, you notice that the slopes are the same, but the y-intercepts are different. Like these 3's here are the same, and the 5 and the 2 are different. And anytime you have slope-intercept equations in a system where the slope is the same, but the y-intercept or the b's are different, you're going to end up with parallel lines. And parallel lines have no solution because they never cross. They never share any points. Yes, no solution. Okay, so when using substitution, if both variables cancel out and you get two unequal quantities, there is no solution, so the lines are parallel. Okay, let's try some more. Use substitution to algebraically find the solution to the system. The solution is where the two lines intersect. So here we go. We have another one here. Let's change to purple this time. Okay, this time I don't have y equals something, but I do have x equals something. X is equal to all of this. So where am I going to substitute it? In place of that x there. Okay, so when I rewrite the equation on top now, I don't have an x in it anymore because I'm taking that x out and I'm replacing it with what x is equal to in the second equation. So I've rewrote my first equation, taking the x out and substituting it with 8 plus 2y. And then I noticed there's no distributive property. So I am on the C step, on the DCMAM steps. And the C step says to combine your like terms. I do have some terms here that I can combine. The 2y and the 1y here. 2y plus 1y is 3y. So after combining my like terms, I end up with another two-step equation. I have two numbers here I need to cancel out somehow and get my y by itself. And the first number I'm going to cancel, that's a y there, just looks weird, is this 8. What's going to zero it out? Minus 8 on both sides. And I end up with 3y on the left side of the equation and 36 on the right side of the equation. And because that canceled out. And the only thing left to do is divide by that coefficient. This dividing by the coefficient at the end is very common. You'll see this a lot. 3 divided by 3 is 1y. And 36 divided by 3 is a 12. So our y value is 12. I'm just going to write that up here in the y position, because we know that the x comes before the y, so it's going to go there. And then once we have our y, in order to solve for x, I'm going to substitute it back in. So this y, I can substitute it into either equation. I'm going to choose to substitute it into this equation. Mainly because x is already by itself, so I feel like that'll just be a little easier to solve. And when I do that, I'm going to have x equals 8 plus 2, but instead of times y, it's going to be times 12, because 12 is our y. And so I do have to do this multiplication first before I can add, according to PEMDAS. Order of operations. Please excuse my dear Aunt Sally. And 2 times 12 is 24. So we end up with 8 plus 24 here. And what is 8 plus 24? Well, that is a 32, which is a big number there. So let's see if we are right. Is x 32, or did we make a mistake? Let's check it out. Yes, it is. We did it correctly. Okay, so we did another example there. And this time when the x was isolated here and substituting for that x. Okay, here's another one. This one has y already solved. Like they're telling you right there, y is equal to 3. That means in our intersection point, our y is a 3, right? But because we know y, we could just substitute it right there in place of that y, and we end up with x plus 3 equaling negative 32. And then to isolate this x, I do need to cancel this 3 out. So let's subtract 3 from both sides. And I end up, negative 32 minus 3 is negative 35. So I end up with negative 35 as the x value. And 3 was already our y value. Bingo. All right, so now we have another one. This one is in slope-intercept form, and one is in standard form. So let's go ahead. What number? Okay, I haven't used this one yet. So we're going to take what y is equal to and substitute it in place of, boom, that y right there. And when I do that and rewrite this second equation, I end up with negative 6x plus 2 times all of this, times y, but you know, y is all of this stuff that I just circled. So I'm putting it in a grouping symbol because I've got to multiply 2 times all of that. All right, and then we have negative 4 at the end here. Okay, so I took my y out and substituted it with all of that. And since that's a lot of numbers, you got to multiply 2 times, we're going to put a grouping symbol there. Now we're on our DCMAM steps. And of course, D comes first, distribute. So we're going to distribute this 2 and multiply that out. So 2 times 3x is 6x. And 2 times this negative 2 is negative 4. And all of that is equal to negative 4 on this side. And don't forget you have this negative 6x over here that we haven't done anything with yet. Okay. And I put a plus here because 2 times 3x is positive 6x. So you do need to put something in between this negative 6x and this 6x. And that's going to be a positive 6x. Now, when we combine our like terms on this one, I could combine these two, but when I do, it's going to zero out. Negative 6x plus 6x is just a 0. So this kind of cancels out. And all we're left with is 2 equal numbers. When both variables cancel out, you're left with 2 equal numbers. The solution is infinite solutions. So I'll just put I, infinitely many solutions. I'll put IS for infinite solutions. Yes, infinitely many solutions is the answer. When using substitutions, if both variables cancel out and you get 2 equal quantities, there are infinitely many solutions, or in fact, it's the same line. So if I were to take these 2 original black equations, put them in my Desmos calculator, I would just have one line graphed on top of one line. What about horizontal and vertical lines? So if one of the equations is a Hoyle line, such as y equals 7, you already have part of a solution if the lines intersect. So since you have the y already, substitute the value of y into the other equation to find the x. That's what we did right here. You know, we had a Hoy line here, and we just substituted it in place of that y there and solved to get the x, right? So here's some examples. We have y equals 2. So I would take what y is equal to there and plug it in right there. If one of the equations is a Vux line, such as x equals 7, you already have part of the solution if the lines intersect. So since you have the x already, substitute the value of x in the other equation to solve for y. So if you get one of those, you're going to take the x value and substitute it in place of the x in the other equation and then solve for the y. So when you get horizontal and vertical lines, basically half of the solution is already there. In the first example, the y is already there. You just had to substitute it in and find the x. And on the second example, the x is already there, and you just had to substitute it in place of x to solve for the y. All right, so here is some pictures of what it looks like when it's one solution, no solution, and infinitely many solutions. What the graphs look like, some sample equations and how to solve them if you needed to refer to that. So great job, y'all. Remember that the solution of one linear equation is any point that falls on the line. Remember that the solution of a system of linear equations is any point that falls on both lines. If the point only falls on one of the lines, it would not be a solution to the system. Remember that if we do not have access to a graph, we can solve a system of equations algebraically using substitution or elimination. And then remember that it is best to choose substitution to solve algebraically when at least one of the variables is isolated all by itself on one side of the equation, like x equals something or y equals something. This includes horizontal lines, y equals a number, or vertical lines, x equals a number. And remember to use the substitution method. We substitute the quantity or expression that is equal to the isolated x or y in place of the x or y in the other equation. So this is, this is the end of the video. And so this takes a lot of practice using substitution to solve systems. But once you get into the habit of how it works and start thinking it through, you'll start seeing why substitution works better algebraically for certain equations. And then when you watch the next video on elimination, you'll see how that method will work better for other types of equations. And of course, the graphing method works for every equation. So if you have a graphing calculator nearby, you can always type those equations in, find that intersection point, or find out if it's parallel lines or the same line to see what your solutions will be. So hopefully you're going to work hard on this and not give up, because it is a little challenging at first, but the better you are at solving equations in we do that toward the beginning of the 8th grade year where I work. But if you are kind of rusty on solving equations, then solving systems of equations will be very challenging for you. So it may be a good thing to go back, rewatch those videos on just how to solve equations, get really good at that, then go and watch the videos on how to solve systems of equations, and then you can practice that and get even better. And then it'll be easy after a while because you won't have to think so hard. All right, so never give up. You're growing. The more you try, the more you practice, the more you will grow. So now it's time for me to say it was lovely teaching you math today. Bye-bye.